Ooh, all right. So what we're going to do is we are going to show that A is invertible. So we have this matrix, and I'm just going to write it down for my own sanity, so I don't have to keep flipping back and forth. So we have 1, 2, 3, 0, 1, negative 1, 2, 2, 2. Okay. So first thing that we want to do is we want to show that A is invertible. Then we're going to find A minus 1 using technology. Then we're going to find the adjoint without technology. Okay, so I'll show you guys how to set it up. It won't be that difficult. It'll be tedious, okay, to do so. All right, then we're going to find A minus 1 using the formula. And then finally, we're going to compare our answers. Okay, so for letter A, and we did this last time, okay, how do we show it? What's an easy way to show that a matrix is invertible? If I remember, I don't remember, that's why I'm asking. So, Jason? Perfect, nice, Jason. We showed that the determinant is non-zero for that matrix, okay? So remember last time we said if the matrix determinant is 0, then it's singular, okay? So for letter A, let's find the determinant of A, okay? And we're gonna do that using technology, right? So in my code, let's go to MATLAB, do a new script. All right, and so A is going to be equal to, all right, we have 1, 2, 3, semicolon, 0, 1, negative 1, semicolon, 2, 2, 2, right? Oh, got 222. And then I'm going to find the determinant of A, all right? And then I'm going to execute, save, and I get -6, okay? I think we actually did this one. I think this might be the same matrix we used another time, okay? So the determinant of A equals -6, okay? And what you guys want to do is when you're doing your homework problems, just write it like this. So that way I know that you guys use technology to be able to do that, okay? And you can just write like MATLAB over top of it. In fact, you don't even need to write the MATLAB. I just know that you use technology to get it. And you could just say that's -6, okay? Which is not equal to 0, which implies that it is invertible. All right. So now that we know it's invertible, we can use technology to be able to get the inverse. Okay. So remember the second part of this, find A minus 1 using technology. All right. So I'm just going to go into MATLAB and I'm just going to say A raised -1, capital A. That would be helpful. And it gives us our inverse right here. Okay. So A raised to -1. That's the same matrix, isn't it? Oh, I got A to the first. It'll be helpful if I put it to the -1. Okay. And let's go ahead and execute that. Good spot, Luke. Okay. So for B, find A -1. Okay. And we're just going to use technology to do that. All right. And then I'll put that back into fractional form. So it's going to be -2/3. All right. And you guys can clearly know like the fractions for these. So it's -2/3, -1/3, 8/3, 8/333. I think that's 5/6. And then 1/3, and then 2/3, and then -1/6, and another -1/6. -1/3, and then +1/3. Okay. So that's easy, right, guys? We know how to do that using MATLAB. No big deal. Okay. Now, next thing we're going to do, though, is we are going to now find the adjoint of the matrix. Okay, so this is something new we haven't done without technology. That means we have to find the cofactors, all the cofactors. Okay, so what that means is, okay, we're going to have to go through and figure out the determinants for each of these. Okay, so it's a little bit sneaky how this is set up. Okay, so I'm going to use this board because we're going to need a lot of work. All right, so now remember when you have a 3x3 matrix, okay, so this is like this entry is -1 to the 1 plus 1. This is -1 to the 1 plus 2, -1 to the 1 plus 3. So remember, that's going to be the signs of the matrix once we find that, right? And then we're going to have -1 to the 2 plus 1, etc. And so when we're done with that, the signs are going to be negative, positive, negative, positive, I'm sorry, positive, negative. So plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. And the only reason I do that is just to make it easy for us, so that way we don't have to multiply by the negative 1 to the power all the time. Okay. Certainly, if you want to do that every time, that's fine. Right. So now what I'm going to do is I'm going to find all these cofactors. Okay. And what I'm going to do is I'm just going to go ahead and find the matrices. Okay. So basically, folks, to find the cofactor, what I'm going to do is for the first position. Okay. So you guys remember what we do is we expand it. Okay. And then we find the determinant of the leftover matrix. So folks, what we're going to have to do is we're going to have to find 9 2x2 matrices. Okay, so not a lot of fun, but it could be a lot worse. And then it's going to have these signs that coincide with those. Okay, so we do this. Okay, so notice I'm going to make this really big matrix. Okay, so for the first one, it's going to be positive from this sign, determinant of 1, negative 1, 2, 2. And then for the next one, it's going to be negative, okay? And what I'm going to do is I'm going to expand right here, okay? So you guys see what I'm doing? Like every time I'm moving along, I'm expanding on that cofactor and I'm finding the determinant that coincides with that, okay? So that's going to be 0, negative 1, 2, 2. So it's going to be 0, negative 1, 2, 2. And then a positive, again, just pulling from right here, right? And then I'm going to have 0, 1, 2, 2. And again, what I did was I just covered up expanding on the 3. I dare not circle it because it's worth more than I am. And I'm trying to like cover it up. It's not going to work no matter what, right? But you guys get the process of this, right? We just have to keep finding all these determinants. Michael?
You don't have to multiply by the.
No, that I think at the end we're going to do that. We'll multiply by this. Okay, so for right now, we'll just find the determinants. And then if we need to, then we'll go ahead and do that. Okay, so so this one's going to be a negative, and we have, so now we're expanding on the 0. So I think it's going to be 2, 3, 2, 2. And a positive. So it's going to be 1, 3, 2, 2, I think. And I'm going to circle the negative 1, and it's going to be 1, 2, 2, 2. It's going to be positive, right? And that's going to be, we expand there. Sorry, it's going to be, try to do it in my head. So 1, negative 1. Circle this. I know I should be able to do that. 2, 3, 1, negative 1. Then a negative, circle that, go 1, 0, 3, 1. 0, 1. And circle the last one, 1, 2, 0, 1. Now at the end, what we'll do is if we need to multiply by these to get the adjoint, okay, because I think we do, okay, but I'm going to hold off until we absolutely know that we have to do that. But I'll just find the determinants first. So
for row 3, column 2, it's 1, 3, 0, negative 1.
Got it. Okay, yeah, because we circled that. So it was 1, 3, 0, negative 1. Gotcha. We catch you. Thank you. Did I copy any of those other numbers up there wrong? There's 36 digits up there, so it's pretty likely that I made a copy error. All right. By the way, I do believe that there's a function in MATLAB that helps us to find the adjoint, which I'll show you guys in a few moments. I think it's literally adjoint A, so you can check your answer. But I want you guys to at least once in your life suffer through and do the adjoint by hand. Okay, sorry about that. Like I said, I'll probably have to do it for the next 30 to 40 years of my life. All right, so let's just go ahead and compute these determinants. Okay. Now remember, compute a 2 by 2 determinant, multiply down, multiply up, and subtract. That's going to be 2 minus 2, so that should be 4. and then multiply down, multiply up, so this is gonna be 0 minus a -2, but then the negative of that, so this should be a -2. And then for the other one, this one should be a -2 as well, so this is gonna be 0 minus 2, that should be a -2. Then over here, that's going to be 4 minus 6 is -2. Opposite of that should be 2. 2 minus 6 is -4. And then 2 minus 4 is going to be -2. Opposite of that should be 2. You're just keeping a bunch of 2s in there, which is fine. -2 minus 3 is going to be a -5. -3 minus 0. Opposite of that should be 3. And then 1 minus 0 should be 1. -3 and -4. So if somebody can, if you guys can check those just to make sure I did all those correctly by finding the determinants. So
The middle of the bottom one is 4. Reverse like
so this guy should be positive
the
4.
the bottom one.
This guy.
Yeah. One above.
Yeah, you should have written 1, 3, 0, -1.
Oh, okay. That like that.
Yeah,
Okay, gotcha. Okay. So this should end up being just a +1, right, folks? Okay, Tyler, does that look better?
Yeah.
Okay, cool. Thanks, guys. Appreciate it. Let's see. That's gonna be, so this is gonna be.
Oh, no,
Right,
yeah.
minus a minus,
Yeah.
and then that minus. Okay, that's okay. No, don't worry about it. Any of those other ones look bad? The whole thing looks bad, doesn't it? Okay. All right. Good thing I didn't give you guys like a 5x5 matrix, right? That would be just better. All right. Now, let's see whether or not this works when we plug it into this formula. Okay, so if it doesn't, then what we might have to do is we might have to multiply by the elements in the original matrix to get the cofactors for this. Okay, so let's see if 1 over the determinant of A times the adjoint gives us what our answer is. Okay, so remember, 1 over the determinant is going to be what? We found the determinant to be -6. Okay, so for D, we're going to take -1/6 times that matrix. Okay, so it was what? 4, -2, -2. 2, -4, 2. And then -5, 1, 1. I feel like we're missing a transpose somewhere in here. Because I feel like, I remember doing the adjoint like 17 years ago when I took the class. And I feel like we had to take a transpose. Oh, it's the transpose of the matrix. Okay. I see. So right here, the word transpose, that would have been helpful for me to be literate and see. So the adjoint is going to be the transpose of that matrix. Okay. So let's see for this. So for C, the adjoint of A is the transpose of the previous. Okay. So, and remember folks, to find a transpose, you just flip the rows and the columns, right? So I'm just going to take the transpose of that animal. So it's 4, -2, -2. 2, -4, 2. And then 5, 1, 1, I think, right folks? Now, what I'm going to do is, I'm going to go ahead and multiply all the elements in that matrix by -1/6. And hopefully that gives us the inverse. Okay, I don't know for certain or not, but just your guys' breed. So I think it will though. 2, 4, 1, 2, 2, 1. All right, so let's see what happens with this. All right, so if I multiply through all the terms, the first one's going to be -4/6, which is -2/3. So that's good, because that one works. -1/6 times 2 is going to be a -2/6 or a -1/3. So that's good. I wonder if I copied that down. I wonder if that was supposed to be a -5/6. So let me check. Or maybe I did a computation error somewhere in here. So it's a +5/6. so that's not good. Can somebody check to see, again, if that should be a -5 when we got that element? Oh, transcription error. Dumb. So this should have been a -5, which means this should be a -5. So I guess in real life, you would just make it and not even worry about it, just copy it over. So, all right, so that's good. That gives us a +5, 6. So it looks like the first row is good. This is going to give us a 1/3. And then we're going to get a +4, 6, which is a 2/3. And then a -1/6. All right, so we're looking good, right? So far. And then finally, 2, 6 is a 1/3. And then that's going to be a -2, 6 or a -1/3. And then a -1/6 for the last one. All right. So looks like we're all good, right? Because it looks like that this is a -1. All right, so that's our inverse by using the adjoint. And right here, this is the adjoint. While you guys are going through, let me show you that I think you can use MATLAB to get the adjoint by using the adjoint function. Okay, so I'm just going to try to type this in. So adjoint A, I think it's that. I don't think it's ADJ. All right, check that. There we go. So that is this matrix, right, folks? That's the adjoint right there. Okay, so when you guys are at home, you can check your answer using MATLAB by using the adjoint function. Okay, but I do want you guys to do it at least once by hand. Okay. All right. So is there any benefit to using the adjoint versus how we found the inverse before? Well, remember before we had to find the row reduced echelon form? Sometimes RREF is a little bit nastier, okay? This is just straight computation, okay, without having to do those elementary row operations. So it could be easier depending upon if you get integer values or not, okay? So I don't know, how many of you guys would prefer to find the inverse this way as opposed to getting row reduced echelon form? Yeah. How many guys would just prefer not to ever find the inverse of a matrix ever? Yeah, there we go. That's the most participation I've gotten all semester. Good stuff. I'm kidding. So, all right. Believe it or not, I actually had a student in another class come in my office asking me how to find the inverse of a matrix. So he's in my differential class and he needs help with it. So anyway, but there are uses for inverses. All right. Last thing I think what I'm asking you guys to do is, what do I ask you guys to compare? Yeah. Compare your answers from part B and D, same, right? Comment. So same, and here's our comment. Inverses suck. If I ask you guys to comment on the exam and you put inverses suck, that's a perfectly acceptable answer, okay? As long as you state that they are the same for whatever response we get, okay? Yeah, it is a comment, right? I didn't necessarily ask for a comment on the mathematical validity or not. So yeah, true. All right. So that's the adjoint. That's how you can use technology to find the adjoint. That's how you can do it by hand. Okay. More than you guys ever care about the adjoint in your life, right? Okay. All right. So what other applications are there? Okay. This is one that that's a pretty solid sort of application. It's Cramer's rule. Okay. Cramer's rule says that you can find determinants to solve systems, okay? So if there is a solution to the system, that is, okay? We know that not every system has a solution to it. So you guys might remember that we're able to solve this sort of system. If it's a 2x2 system, we could do like elimination or substitution and eventually get to these manipulatives, okay? So at home, if you want to derive these, it'll probably take you guys a few minutes to do that, all right? But I want you guys to notice, and I know it's tough to see, but for those of you guys that have the guided notes, you could probably see that the numerator and denominator are just determinants. Okay, so this is like a 2x2 determinant, as is this. Both of the denominators are the same determinant that we're used to seeing. Okay, that's actually the determinant of the coefficient matrix. All right, and so Cramer's rule says that if we just find the determinants of these forms, B1, B2, where those are the constant matrices, A12, A22, where those are going to be the coefficients of the left-hand side, and then similarly, A11, A21, B1, B2, that'll give us this, and we divide those out, that'll find the solutions to our system of equations, all right? This is actually a really efficient method, okay? A lot of computer algebra systems will use this method because there's no row reducing, you just plug it into the formula, okay? Now, the question is though, how can we expand that to a 3x3 system, okay, or even more, okay? And I'm going to show you guys that in the next example, all right? So these are going to be our formulas, and I'm going to go ahead and just help you to, or we're going to work together to be able to solve this by using Cramer's rule, okay? So let's use Cramer's rule to solve this system. So I'm going to start by finding the determinants of three matrices, okay, A1, A2, and A. Okay? And we'll find that the solutions are really easy for this, okay? So we need A1, which is equal to B1, B2, so that's 5, 1. And then A1, 2, A2, 2, okay? So that's going to be first row, second column, 2, 1. So does everybody see how I set that up, guys? B1 and B2 are going to be the constants on the right-hand side. And then A1, 2, A2, 2 are the coefficients of x2, okay? Over here, A1, 1, A1, 2, so A2 is going to be equal to 1, negative 1. And then the constant vector, or the constant column matrix, 5, 1. Finally, for A, that's just the coefficient matrix of the left-hand side, 1, 2, negative 1, 1. All right, we know how to find the determinant, okay, really easy. Okay, so if we find our determinants, first one's going to be 5 minus 2, I think that's 3. This is going to be 1 minus a minus 5, which is going to be 6. And then finally over here we get 1 minus a minus 2, which should be 3. To find x1, x1 is the determinant of A1 divided by A. That's determinant of A1 divided by determinant of A. And we know determinant of A1 is 3, determinant of A is 3. 3 divided by 3 is 1. For x2, that's the determinant of A2 divided by A. And that's going to be equal to 6 over 3, which is 2. So that's the solution to this system. And of course, if you don't believe me, plug in 1 and 2 and see if it works in this system. Okay. So I know that 1 plus 2 times 2 is 5. Negative 1 plus 2 is 1. So it seems to work really nicely. Okay. So this is a really simplistic way to be able to solve a 2x2 system of equations. Okay. You can imagine if the coefficients are a lot nastier. Okay. Like I know a couple of you guys are my differentials class, and last week I think we had a problem where like the answer ended up being like negative 8 over 425. This would have worked really nicely to solve that system. Okay, instead of like I think we did the cancellation method, and I know you guys were bored as stuff. Sorry, I'm being recorded. I was going to say something else, but you guys were bored as stuff while I was solving it. But yeah, but that's a nice way to be able to solve something like that. Okay, so is that kind of cool that you guys can solve systems that way? All right, kind of cool, right? Better than the adjoint of a matrix. Everything's better than adjoint, except physics. Good thing I didn't say that while I was being recorded. Now, what if it was a 3x3 system? Okay, well, what I can do is I can do the exact same process. And I want you guys to notice that all we're doing is for A1, the first column is the constant matrix on the left-hand side. In A2, the constant matrix is the second column. So basically, if I had 5 variables, I would just go ahead and put the coefficient matrix together, except the fourth column would be the constant matrix, okay? So basically, you just copy the coefficient matrix, and whichever subscript you're on, you just replace that column with the constant matrix on the right-hand side. That's the easiest way to remember, okay? And then you just plug it into these formulas, okay? So det A1 over det A, det A2 over A, det A3, okay? So I'm going to set these up, and we're just going to use MATLAB to compute the determinants of these things, okay? Because with 3x3s, we know we can do them. They're just a bit painful, right, guys? Because we have to rewrite the columns. And it usually takes about a minute to do it. Okay. All right. So for this example, let me go ahead and start by setting up A1 A2, and A3. And then I'm also going to go through and set up the determinant of A. All right, now determinant of A1, since it's the first of these, I'm going to replace the first column with 11, 11, and 3. For A2, I'm going to replace the second column with 11, 11, and 3. And for the third, A3, I'm going to replace the third column with 11, 11, and 3. Okay? So you guys see how that works, guys? You just take the constant matrix and you just move it along. Okay? The rest of it, we're just going to fill it in with the coefficient matrix on the left-hand side. Okay? So that's going to be 4, -4, -6, and then 4, 6, 0. And then over here we have 3, 4, 6. So basically, folks, all I did was I just copied down this coefficient matrix into there, except for whatever subscript we were on, replace that with the constant matrix column. For A, I just literally copy over the constant matrix. Okay, so or the coefficient matrix, excuse me. So that'll be 3, 4, 6, 4, -4, -6, and then 4, 6, 0. All right, now what we're going to do is we're just going to use good old MATLAB, and MATLAB's going to help us to find these determinants. Okay, and when you got what I'll do is, since we're using technology to do this, I'll put in like our accepted symbol for technology, or as best as I can. So now I'm going to need y'all's help. All right, so I don't need this anymore. So I'm going to call this, I'll just say A1, A2, A3, and A. Okay, so if you find folks could remind me, could somebody read off A1 and read it across according to rows, if you guys could.
11, 4, 4. 11, -4, 6. 3, -6, 0.
Got it. Okay. And then I'll go back up and suppress them in a minute. Okay. A2.
3, 11, 4.
4,
11, 6. 3, 0.
Got it. A3.
3, 4, 11.
Oh, sorry. 3, 4, 11. Go ahead.
4, -4, 11. 6, -6.
Okay. And then finally A.
4, 4. 4, -6. 6, -6.
Okay, got it. You should be like one of the people that calls out at bingo. So it was soothing. Very nice. All right. Now I'm going to find the determinants of each of these. Okay, so I'm going to say det A1, not DQT, det. So remember to find the determinant, det A1, and then I'm just going to copy this because I'm efficient / lazy. 3, 2. All right. And then let's see what we get out of this. Okay, so these are our numbers. Okay, so I'm going to raise this up. All right, so I get 252, 126, 252, 126. Let's see if it works. No. 6 extra steps. I think I'll live. 378, 300. Okay. Now, what we can do is we can find the solutions by dividing A1 by A, A2 by A, and A3 by A. And that should give us the solution to the system. Okay, it might not be nice, but it is what it is, provided that we didn't copy anything down wrong. Then what I'll do, folks, is I'll go ahead and create a new matrix to RREF this thing and see if we get the same numbers. Okay, so we can check the answers. All right, so I'm going to say x1 is going to be equal to the determinant of A1 over A. And it was 252? 252 over 300. X2 is A2 over A, which was what was it, guys? 126 over 300, okay. Which is actually kind of cool because, yeah, I was going to say 126 times 2 is 256. Nice. And then for A3 over A, 378. 78. Is that times 3? Yeah, that's 3 times this number, I think. So funny how math works, right? It's almost like there's some sort of pattern in math or something. So, all right. Whatever those numbers turn out to be, I don't know. All right. But let's go ahead and I'll RREF this animal. So I'm just going to take A. And let's do this. I'm going to get rid of all this because I don't need it anymore. Let's comment that out. And then I think the constant was what, 11, 11, 5, 4? Was it 11, 11, 3? I was off by 1. Put on the teacher evaluation. And then I'm going to RREF this thing. All right. So let's see what we get out of this. All right. So can somebody in their calculators just randomly pick one of these? I don't care which one. And then just let me know what you get out of it. It looks pretty good. It seems right, yeah, just by eyeballing it. First one makes me worry a little bit. But did I figure any of them out?
First one I got 0.84.
0.84. So this would be 1.68, or I'm sorry, half of 0.84, 0.42. Okay, well, that's good. And then that last one, did anybody do 378 over 300? That doesn't look right.
Yeah,
though. 1.26. All right.
You were supposed to put -4, you put -6 in the middle one.
Got it. Where is it, Lily?
-6 is supposed to be -4. Yep.
Oh, that'll do it. And I bet you up here. Word. Okay, so let's go through. That's okay. Good catch. Good catch. Right. So, yeah. This should be A for right here. This should be. Hold on. That's okay, right? It's just this one. It should be a -4, right, folks?
Yeah.
Okay. So that's going to change everything, right? Okay. So, oh boy. That's okay. All right, so let's go back up here. Yeah, right? Yeah, I know. Well, these numbers are a lot sexier at least. So that's nice. But these determinants, I still don't like the determinants. Because notice that, well, wait, this changed to 252. Oh, that's hot. Oh, that's definitely cool. Okay, I dig it now. All right, so, sorry, guys, I'm getting all giddy. There we go. Okay, that's it. That's what happened. See, one stupid error, right? All right. Let's try this again. I should have just erased the denominators, right? That would have been more efficient. All right, so this was 378. This was 126, and this was 252, right, folks? That's a lot better. And then let me check the RREF again. Oh, nice. So, so from our RREF, X1, X2, X3, we got 1, 1/2, and 3/2. Okay, cool. So that makes me a lot happier that it actually works. So good stuff. Cool. All right, and good job, by the way, spotting that silly little error. All right. All right. You guys can imagine that once we start getting into a lot bigger systems, this might be more efficient than trying to do RREF, right, guys? Because it's strictly computational. The bad news is finding the determinants, right, guys? Determinants are a little bit nasty to find. So go ahead, Michael.
Does it matter? So in MATLAB, you have A as the 4x4 or 4x3, and then you'll set it as a 3x3.
Right. So right here, this was just to find the RREF at the end. At the beginning, though, what happens is MATLAB overwrites them. So this is the most current instance. So what it'll do is it'll run everything up here as separate from down here. Okay. So when you guys do your homework, You don't need to do this. That's just to check the answer, okay? So does that answer your question, Michael? Okay, cool. I just want to make sure I was answering it correctly. Okay, got it. All right, other questions, folks? Okay, so that's Kramer's rule. We've done the adjoint, okay? Let's see, what else do we have? All right. This is a problem for those of you guys that suffered through Calc 3. All right, you might have seen how to find the area of a three-dimensional object or two-dimensional object in space, okay? So if we have an area of a triangle, okay, what we can do is we can actually project that onto the XY plane. That's what this is really doing, okay? I'm not going to go through the proof of any of this because if I do, we're going to be here for the entire class proving these, all right? But what we're doing is we're just going through and projecting it. So it's going to be 1/2 of the determinant of x1, x1, y1, x2, y2, x3, y3. This is just going to be the coordinates of the vertices, okay? We could actually extend this to be able to find the area of a parallelogram in space as well, because we know parallelogram is just base times height, okay, if we wanted to, all right? So let me show you guys how we can find the area really quickly just by doing this. And of course, we can use MATLAB to do it. It's either going to be positive or negative depending upon the determinant. If the determinant's negative, we're going to multiply by a negative. If the determinant's positive, we don't change the sign, right? Because we don't want negative area. Otherwise, we have a black hole, which might be similar to finding the adjoint of a matrix because we all get lost doing that. Yeah, you can just do the absolute value of that. And I think that's what we did in Calc 3 when we did it. We just took the absolute value. I'm just following what's in the textbook because I know some of you guys look online at the textbook, so I just want to be consistent. All right, so let's find the area of a triangle with those vertices. All right, if we were to do this by hand, it wouldn't be as difficult. We just have to find the height. We might have to use a law of sines or cosines, so it might be a little bit nasty, but this can work nicely. Okay, so that's going to be equal to plus or minus 1/2 of the determinant. I'm just going to take the points, so 1, 0, 2, 2, 4, 3, and then I'm just going to stick ones right here. Now in MATLAB, I'm just going to use our MATLAB to find that. So let's see. Let's call it A. All right. And okay. So A was 101, 221, and 431, right? Okay. I'm going to find the determinant of A. Right. Now notice I still have to multiply that by 1/2. Okay. So in MATLAB, this is going to be plus or minus 1/2 of -3. We're going to choose the negative because we need to multiply it out. So this is just going to be equal to 3/2. Okay. It's going to be 3/2 of whatever the unit is. So I'm going to say unit squared because we are trying to find the area of this thing, right? That's it, okay? So it's a lot easier than maybe finding like a bisection and then maybe using like the law of sines or cosines to be able to find the areas, okay? You guys probably use law of sines and cosines a lot in your physics and your engineering classes, okay? This makes it a lot easier, okay? Or maybe, so, Sean?
So if I use this in Calc 3, so
And me personally, I wouldn't mind because now realistically, you guys are going to find the cross product of this, okay? Because I'll ask you guys to use like vectors, etc. Okay, but this is another way to do it. I probably will ask you guys to find, you know, that determinant of that by using like the vector method of it, which is fine. Okay. All right. Other questions, guys? Nice and easy. Okay. We wish the entire exam was this. We'd be fine. All right. If 3 points are collinear, in other words, they fall on a line, then the determinant of what we just found is going to be 0. Okay. And you guys remember, were we able to find the equation of the least squares line on our previous assignment? Okay, we had to use like a weird formula with a transpose and all that stuff. What we can do is we can just go ahead and see if the determinant's 0 and they're collinear. And that means that they all fall on the same line, which means there's an equation of line that passes through all those 3, which we'll find in a moment. Okay, so let's just show that these points are collinear. Okay, so to do that, what I'm going to do is I'm going to construct a matrix or a determinant, and I'm going to use the points. So I have 0, 1, 2, 2, 4, 3. Okay. And Actually, that doesn't make any sense because that's the same points we just used, isn't it, folks? And we know that that's not collinear at all because those are the vertices of the triangle that we just found right here.
1, 0, not 0, 1.
Oh, okay. That's even better. So, yeah. Yeah, clearly, like every one we go up by 2, we're going up by 1, right? So clearly it's on a line. Okay. This will be a 1, 1, 1. So let's see if the determinant of this animal is 0 by using our MATLAB stuff. And the good news is, boy, I must have been really smart, like making this problem. Because now all I have to do is just flip these two numbers around, make that a 0, 1. And I get 0 out of the determinant. Okay. So by using some technology, okay, we find that the determinant is 0, which means that the points are collinear. Wouldn't that also mean that the area of the triangle with those 3 vertices is 0 as well, right? Well, duh, it makes sense because if they're all on the line, there's no area to that triangle. So this is a way for you guys to verify that this is collinear by thinking about it in context of an area. Okay, all right. So that was pretty easy. Yeah. All right, let's see, what other fun do we have? Equation of a line, okay? So what we would do is if we had 2 points, we just replace x and y with 2 points, and that'll find the equation of a line that passes through 2 points, okay? So you guys remember in Calc 1, the tangent line problem, everybody did that more than they ever care to do it, all right? You had to use the y minus y1 equals mx minus x1 for it, okay? Well, what we can do is we can formulate the equation of a line like this, okay? And I'll show you guys pretty easily how we're going to do that in MATLAB. So we want to find the equation of a line through these 2 points, okay? So what I'm going to do is I'm going to find the determinant of xy1 and then x1, y1, which is 2, 4, 1, and then negative 1, 3, 1. All right. Now, let me go, and this should be equal to 0, by the way. All right. So I'm going to use MATLAB. All right. I am going to use x and y, and I think it'll work without making a symbolic variable, but if we need to, I will. Okay. So it was xy1, and then was it 4, 2? 2, 4, 1. Okay. And then was it 0, 2 or negative 1, 3? Negative 1. Boy, it was totally off there. Okay. And let's find the determinant of A. All right. So I'm hoping MATLAB will do it. No. So what you guys are going to have to do is you're going to have to do a Sims X and Y in here. Okay. All right. Anytime that you have a free variable, okay, sorry about that. MATLAB just doesn't like those. So just define X and Y to be symbolic variables. Okay. I know most of you guys have done MATLAB before, but if you haven't, okay, because you just haven't. All right. So I run it. Okay. And so I get this. Okay. So that's going to be my equation, x minus 3y plus 10 equals 0. And remember, folks, that's the general form. Okay. So ax plus by plus c equals 0. Okay. So that's a really nice way that if you ever need to find the equation of a line, especially if you have really nasty points, okay, like square roots or e's or something like that, you can just throw in the determinant and MATLAB will do it for you. Okay. So when we compute MATLAB, okay, so that's what we get. All right. So any questions about that, folks? It's pretty cool that we can find the equation of a line just by using MATLAB and a pretty simplistic formula. And I want you to notice how close most of these formulas are, right, guys? It's like x1, y1, 1, x2, y2, 1. I said the same thing up there, except we just use general xy. Okay. All right. So what other fun do we have? Equation of a plane. Okay. So for those of you guys that have suffered through Calc 3, you know that this is a typical problem. Okay. I can't think of anybody that has taken Calc 3 that hasn't found the equation of a plane. Okay. If you haven't, then go back and tell your teacher since I'm being recorded. All right. But yeah, I know, right? And I absolutely know that I made you guys do the equational plane until you were sick in the head of doing it. So, but if we just substitute the values back in, okay, and instead of having a 3x3 system, we have a 4x4 system. We can go ahead and find the equation of a plane. I do need to make a symbolic variable z though, right, guys? So we have x, y, and z. All right. So when I set this up, I'm going to have the determinant. And it's going to be x, y, z, 1, and these are all ones. And then I just fill in the points. So 1, -2, 1, 1, -1, -1, 7, and then 2, -1, 3. Now, I am going to need your guys' help reading that one off. Obviously, I can't even memorize a 3x3, so there's no hope for me memorizing a 4x4, right? Remember, whenever you guys are doing this, fill in the symbolic z, okay? So we have x, y, z, 1, okay? And then can somebody read off the other 3 rows for me, please?
1, -2,
Uh-huh.
1, 1,
Hold it, 1, -2, 1, 1. Got it, Luke, go ahead.
-1,
Uh-huh.
-1,
Mhm.
7, 1,
Got it.
and 2, -1, 3, 1.
All right. Now I'm going to find now the determinant of this matrix, okay? And it gives us this as the equation of the plane, okay? So you notice it doesn't give us it to us in a nice order. We'd like it as x, y, z. I don't think it matters though, right, guys? So we're going to get that 10y minus 4x minus 3z plus 27 equals 0. If you don't trust that that's the answer, couldn't you just take any one of the points and plug it back in? So remember we had the point 1, -2, 1. That should work, right? And so as a check, I could plug in 1, -2, 1 back in. So -2 would go into y, 1 would go into x, 1 would go into z. Okay. So this would give me -20 minus 4 minus 3 plus 27 equals 0. And I think we get 0 equals 0 out of that, right? Because 20 minus 4 minus 3 is -27. All right. So that's a way you guys can at least check to make sure that you get the right answer. Okay. By the way, for those of you guys that have suffered through Calc 3, okay, why do we even care about a plane in space? Like, what's one of the purposes of finding a plane in space? Yeah, right. Well, I know you guys did it. I absolutely know you guys did it. So, what we could do is, let's say we have like a 3-dimensional function. Okay? And for those of you guys that don't have to take Calc 3, don't worry about that. Let's say I have a 3-dimensional function like an elliptic paraboloid. And let's say I have a point, and I construct a plane that's tangent to that point. Couldn't I approximate the value in the neighborhood of that point using the plane? That's a local linear approximation, okay? How many of you guys remember local linear approximations from Calc 1 or Calc 3 or something like that? Okay. Now, what if it was like a really nasty function that had like a sine and an e to the x in it, okay? That's where this would be helpful, okay? For my computer programming people, if you're a computer scientist, these things, local linear approximations, increase your runtime exponentially, no pun intended, okay? Because this thing, I mean, if you guys really wanted to, you guys can compute this all day, right? But if I said, figure out, like if I said sine of xy, where x is equal to 5 and y equals 27, you got no shot, right? Nobody in the room knows what the sine of, what's that going to be, 135 is? Okay, I don't know what the sine of 135 is. But if I found a local linear approximation, I could plug those points back in and get an approximation really nicely, as long as it's in the neighborhood, okay? For any of you guys that are doing like computer programming in your master's programs, okay, usually you're gonna have to use a linear approximation to increase your runtime if you have a significant amount of data, all right? I know we're almost at break time and I wanna be sensitive of that, but just letting you guys know, I was helping a grad student with some space data. And they had so much data that they literally had like, I think like maybe over a billion data points. And they were trying to plug it into this really nasty formula and the computer couldn't do it because the formula was transcendental. So I suggested, well, just use a linear approximation. and they pumped it into C++ and it cranked it out in like less than a minute, okay? Like he let this thing run for like 3 hours one time and it didn't make a dent in it, okay? And that was only with like about a quarter of the data just as a test, okay? So just letting you guys know, for those of you guys that are comp sci people, local linear approximation, and math people and engineers, but local linear approximations are one of the most efficient ways to try to process large amounts of data, okay? Is anybody interested in data science, like getting a career in data science in class? You probably make the most money out of anything being a data scientist, which makes me think about why I'm being a teacher anymore. But data scientists, they take that huge magnitudes of data and they process it efficiently. So that's why a data scientist has to be good at math, good at programming, good at algorithms, and a lot of times they have to be good at business, okay? So I've always thought about going back and getting my doctorate in data science, just because that's the stuff I love is optimization. So anyway, I didn't mean to go off on a tangent, but I did go off on a tangent. That might be the funniest thing I've said today. It's probably not that funny, so. All right, so any questions I can answer about applications? I think that was the last one, right? There's nothing after that. Is there? Nope, that's it. Okay. All right, probably on the exam, I'll probably have like something like this. And like I said, on the exam, you guys can use MATLAB, okay? There's gonna be problems where I say you can't use MATLAB, okay? But on any problem that I say you can use MATLAB, you can certainly use MATLAB on those, okay? They're gonna be mainly be for the types of problems like this where they're application problems, okay? All right, folks, get up and stretch out for about 10 minutes. We'll come back, and when we come back, I'll show you guys some more of the stuff with respect to our MATLAB assignments. Sounds like fun? No? Fine.
Yeah.
Oh, you're a good liar, Mr. Castillo. I like it.
So there's gonna be like only one question.